Hi and welcome to the next of our HL bonding videos. Today we're going to be looking at molecular orbitals and hybridization, so looking at those s and p orbitals and taking it just a little bit further. So we know that compounds will form bonds in order to achieve a more stable state, that is, to complete their octet. Okay, so when we talk stability, this generally means that when things are bonded, they're in a lower energy state than when they're not. When a covalent bond forms, we know it forms from the sharing of electrons. Okay, so in this H2 molecule, the sharing of a 1s1 and a 1s1 to form a molecular orbital. So the overlap of these orbitals from two atoms form a molecular bonding orbital. So we know in this case that the hydrogen atoms would have s orbitals. When they come together, that s orbital from each joins to form a shared region known as a molecular orbital, and it is lower in energy than the two that it was derived from. So sigma bonds, we know, are formed from the end-to-end or head-to-head overlap of two atomic orbitals, be an s and a p, 2s or 2p. So this is along the axial overlap, producing high electron density in the shared region. The pi bonds from the sideways overlap, okay, these are unhybridized orbitals, as we will come to learn. They are p orbitals. The pi bond is the region where these overlap, again causing a high electron density between the two atoms. When we talk hybrid orbitals, what we're saying is this is the process of essentially mixing the atomic orbitals as they approach to form the new bonding orbital. There's no energy change involved in forming the hybrid orbital, so the hybrid orbital isn't any different. When we mix a certain number of orbitals, we will get the same number of bonding orbitals or hybrid orbitals formed. That is, if I mix an s and a p, this is two orbitals mixing, so I will get two hybrid orbitals, which will be sp hybridized. Okay, and this is what we see here. An s and a p orbital coming together to form a sigma bond. We're going to form sp hybrid orbitals. Okay, so the types of hybridization that we need to cover are sp, sp2 and sp3. So we can see here this is the coming together of two orbitals, this is 3, and this is 4. So essentially what we're seeing is the mixing of a number of non-equivalent orbitals to form an equivalent number that all have the same energy or are equivalent in the type of orbital that they are. We don't see, so we have 1s and 3p. We don't see hybrid orbitals forming between 1s and 2p. When we have newly formed energy orbitals, we say that they are degenerate. Okay, this means that the energy is between the two orbitals that were combined, okay, but they're all the same. So hybridized orbitals will have their own shapes, different to the two that were mixed. Generally, this means when we're talking S and P, because of the spherical nature of the S and that bilobe nature of the P, that we see one large lobe and one small lobe. Okay, so the large lobes mean that the orbitals can overlap, forming stronger bonds than the non-hybridized orbitals. What we see here is an example of tetrahedral geometry where we have 1s and 3p. Therefore, we will form 4 hybrid orbitals, and it will be sp3 hybridized because we have 1s and 3p. So hybridization will generally occur in 2 stages. We have unpairing of paired electrons. This is generally from the s orbital, and then promotion of an electron, so an s electron to a p orbital. The hybridization or mixing, okay, all the orbitals become degenerate, the same energy. Empty orbitals will remain hybridized at the original at the level and are available to form pi bonds. So let's have a look. So if we have a look here, we have this one in the ground state. We get unpairing and promotion of this. So now we have one here using our Aufbau diagrams and two here. So these are our p orbitals and our s orbitals. The hybridized orbitals are between the energy of the s and the p. They're sort of halfway between. Okay, so we can see that even up until D, we have Sp3 hybridization here, 1, 2, 3, 4, 5. These are going to be promoted into our hybrid orbitals, where 1, 2, 3, 4, 5 are spread out unpaired. So if we look at the hybridization in boron, remembering, okay, so we've got boron is element number 3, so we have 1s2, 2p1. We have unpairing and promotion, so we get 2s1 and then 2p2. These will hybridize to form the sp2 because I have 1s and now 2p orbitals. I will have sp2 hybridized and then one orbital will remain unhybridized. If we see for carbon, if carbon forms 4 bonds, we're going to need the 4 electrons. It has 4 valence electrons. Unpair and promote to get 3 in our P. We will now have Sp3 hybridized orbitals, each with 1 electron, ready for pairing to form the bonds. If we look at beryllium, 2 electrons, 1 stays in the S, the other in the P, so we get Sp hybridized. So essentially what we're doing is looking at the number of bonds, and it will be Sp1 minus the number of bonds. So if carbon has 4 bonds to it, it will be Sp, and because the bonds are 4, 3. 3 bonds, we have Sp2, okay, so this would be trigonal planar. And then we have Sp if it's going to be linear. Determining the type of hybridization, draw the Lewis structure, determine the electron pair geometry, the number obtained in, so consider a multiple bond as 1 domain as normal, count the number of domains, okay, and the number is the number of hybrid orbitals you get. So if we look here, we have 2 domains, so this will be Sp. 3 on a trigonal planar will be Sp2, which is 3 hybrid orbitals. Tetrahedral will be Sp3, and that's as far as we go. Even though we cover trigonal, bipyramidal, and octahedral shapes in HL, we do not need to understand their hybridization. So if you have an Sp3 hybridized carbon, your bond angle is going to be 109.5. If you have an Sp2 hybridized carbon, then you're going to be looking at bond angles of 120. Sp will be 180. So when we have Sp3 hybridization, we have 1s and 3p orbitals. This is the mixing together of 4 orbitals in the valence shell of carbon. The valence shell is in shell 2, so 2s, 2px, 2py, and 2pz. Remembering that x is our horizontal, y our vertical, and z our 3-dimensional through the middle there in our plane. Okay, so each of these, we mix these 3 p orbitals and the s orbital and form 4 sp3 hybridized orbitals where we have 1 big lobe and 1 small lobe. Okay, so if we have 4 bonding pairs, it's going to be tetrahedral, 3 bonding pairs and 1 non-bonding pair, trigonal pyramidal, and 2 non-bonding pairs and 2 bonding pairs. Okay, it doesn't necessarily relate to the shape because remember, these orbitals can hold a lone pair. So we could have an Sp3 hybridized nitrogen where we have the lone pair and 3 bonding pairs on ammonia. Okay, but if we have 4 negative charge centers around the central atom, we have Sp3 hybridization. So we can see a typical tetrahedral bonded carbon in methane would be Sp3. Also, the bonding that we see in hydrocarbon molecules for organic compounds is Sp3 because we have 1, 2, 3, 4 bonding domains around that central carbon, okay, negative charge centers, it's going to be Sp3 hybridized. As I mentioned before, we also see Sp3 hybridization in ammonia. We have the 2s, and then we see unpairing and promotion. With this, we have the lone pair, so we end up with a lone pair in one of the hybrid orbitals and then the unpaired that will form the covalent bonds in the other 3. Okay, so this is 1 non-bonding pair and 3 bonding pairs, but still 4 negative charge centers around our central atom, so still Sp3 hybridized. Sp2, we're now talking 1s and 3p orbitals. This we will usually see in our trigonal planar geometry with the empty orbital sitting through that central atom in an axial position. Okay, so this is the mixing of the 2s, 2px, and 2py. And we get these 3 being mixed together to form degenerate orbitals. So therefore we have Sp2 pointing to the vertices of an equilateral triangle. They're identical. The bond length, strength, and angles are all identical for each of the 3 bonds. When we look at examples of Sp2 hybridization, okay, we can see here that in this compound here, we have the formation of a double bond. So we have the double bond counted as 1 charge center, and then the 2 single bonds as 2. So that gives us 3 negative charge centers around that carbon. So we have an Sp2 hybridized carbon. Sp, we now are blending only 2 orbitals. So we have the hybridization with an S and a P, leaving unhybridized orbitals. When we put the 2 Sp orbitals together, they will repel to be as far apart as possible, so we will get a linear shape. The 2 orbitals are identical, so the bond length and strength are identical for the 2 different bonds. If we have a look at this, things such as beryllium, or our alkyne bonding, where we have a triple bond, and then the hydrogen bonding to each side of the nitrogen. This carbon here has 1, 2 negative charge centers, so it's Sp. Same with this one, 1, 2, Sp, and then the beryllium is the same. So if there are 4 electron domains, it's Sp3, 3 electron domains, it's Sp2, and 2 electron domains, it is Sp. You will generally be asked from a structure to state the hybridization. You may also be asked to draw an Aufbau diagram, the ones where we see our S and our P going into the degenerate Sp hybridized. Okay, remembering that we will end up with all unpaired unless there's a lone pair in our hybridized orbitals, and they are all the same energy. Okay, that's it from me for hybridization. Next up, just a quick recap of delocalization, and we will be finished HL bonding.